linear least squares analysis. In this course, you will often have the opportunity to fit a model to the experimentally obtained data points. For example, here you have 4 data points for relating x to y, relating y to x. It looks like a straight line. An equation of a straight line is y equals to ax plus b. And where a is the slope and b is the offset. And we don't know what a and b are. With different a and b's, you generate different lines. And one of those lines is the best fit. Here, for example, number 2 is the best. And so the linear least squares method allows you to find the optimal a and b parameters in order to fit the data the best way. The method is not only appropriate for fitting straight lines. Here you have data points that look like a sinusoid with increasing bias. An equation for that is this, where a is the amplitude of the sinusoid and b is the slope of the increasing bias. So we also want to be able to find the a and b parameters. And it turns out the best is 1 and 0.5. And the method is also appropriate in finding the unknown parameters for a polynomial, such as these parameters a0, a1, and a2 in this quadratic formula, and higher order polynomials in similar form. And as well as for other models as well. The only requirement is that the unknown parameters a and b appear in the equations linearly. For example, in here, a and b appear linearly. There's no square term, no square root of a, etc. So what constitutes the best fit? Here we have 3 data points, and red line is the hypothesized best fit. Now you can formulate the error as the distance from the data point to the line, vertical distance. And then what we're doing is that for each data point error, EI, we square it and sum all the EIs together. So this J tells us about how far is this line from all the data points. And our goal is to find an A and B that minimizes this total error J. We can formulate this linear least squares problem in a matrix formulation. To do this, we take each data point and then organize it right in this way. For example, the first row here of this matrix equation basically says y1 equals to a11 times little a1 plus a12 plus little a2. And similarly for the second row and the third row, etc. So each row will correspond to one data point. And because the data point and the model do not correspond exactly, and there will be some error, you can add the error here, which is the difference between the data points and the model. And so in this formulation, then the error, big E, and the output, big Y, and the matrix A can be used to formulate the problem. Specifically, the total error can be now written as the inner product between this error vector E with itself. In the matrix equation, the best fit solution for the parameter can be obtained using this formula, which is A transpose times A inverse multiplied by A transpose and then multiplied by output vector Y. And this formula is obtained by solving for A that make dj by dai equals to 0 for all I equals to 1 to n, where n is the number of unknown parameters. And this can be easily implemented in MATLAB in this way. Well, previously, we have assumed that all the data points are exactly similarly reliable. But in some cases, some data points are more reliable than others. In this case, we can weight the errors. For the data points that are more reliable, we add more weights. And the data points that are less reliable, we put less weight. And to do so, what we are doing is that we can formulate a weighting matrix then with a diagonal consisting of the weights for the individual data point. And then we can multiply the original vector, output vector y, by the weighting matrix, and original data matrix A multiplied by the weighting matrix, and obtain YW and AW. And the solution to minimizing this weighted least squares problem is this formula, which looks exactly the same as the previous formula, except that A is replaced by AW and Y is replaced by YW. And so, in this video, we've talked about using linear least squares method to fit data. And by putting the data, the model in the matrix form, you can easily obtain it by plugging it into MATLAB. Thank you.